Morning students. So in this video we will see about bootloaders, booting process and bootloader. So in an embedded Linux system, the bootloader has two main jobs. One is basic system initialization and the loading of the kernel. So in fact the first job is somewhat subsidiary to the second, in that it is only necessary to get as much of the system working as is needed to load the kernel. So when the first lines of bootloader are executed following power on or a reset, the system will be in very minimal state. So the DRAM controller will not have been set up, so main memory is not accessible. So that is your dynamic RAM. Likewise, other interfaces also not been configured, so storage accessed via NAND flash controllers and MMC controllers and so on. So typically the only resources operational at the beginning, they are a CPU core and some on-chip static memory. As a result, system bootstrap consists of several phases of code, each bringing more of the system into operation. So the early boot phase stops once the interfaces required to load a kernel are working. That includes main memory and peripherals used to access the kernel and other images, that is they are able to work. So the final act of the bootloader is to load the kernel into the RAM and create an execution environment for it. So the details of the interface between the bootloader and the kernel are architecture specific, but in all cases, passing a pointer to information about the hardware that the bootloader knows about and passing a kernel command line, which is an ASCII string containing essential information for Linux. Once the kernel has begun start executing, the bootloader is no longer needed and all the memory it was using, it can be reclaimed. So a subsidiary job of the bootloader is to provide a maintenance mode for updating boot configurations, loading new boot images into the memory, so that is running diagnostics. This is usually controlled by a single command line user interface, commonly over a serial interface. Once you move away from a simple linearly addressable storage medium like NOR, flash, the boot sequence become a complex multi-stage procedure. So the details are very specific to each system on chip and generally they follow each one of the phases. So that is if you are using this NOR, that is flash, that is any flash memory NOR or NAND flash or managed flash, you will be having a boot sequence. So the first, in olden days, the boot that is the it was necessary to place the bootloader in non-volatile memory at the reset vector of the processor. So you can see here in boot in the olden days. So in the reset vector of the processor, that is in the NOR flash memory. So it was common at the time and it can be mapped directly into the address space and it was the ideal method of storage. So whenever a button reset is pressed, so this boot sequence, it is loaded in the NOR flash memory. So the bootloader is linked so that there is a jump instruction at that location, so that points to the start of the bootloader code. From that point it can initialize the memory controller so that the main memory, the DRAM, that is dynamic RAM, becomes available and copies itself into the DRAM. So once fully operational, the bootloader can load the kernel from the flash memory into the DRAM and transfer control into it. In the absence of reliable external memory, the code runs immediately after a reset or power on, as to be stored on chip in the SOC. That is known as the ROM code. So it is programmed into the chip when it is manufactured. Hence the ROM code is proprietary and cannot be replaced by an open source equivalent. So the ROM code can make very few assumptions about any hardware that is not on the chip, because it will be different from one design to another. So this applies even to the DRAM chips used for the main system memory. So consequently, the only RAM that the ROM code has access to its small amount of static RAM found in most SOC designs. So the size of SRAM varies from as little 4 kilobytes up to few hundred kilobytes. At the end of this phase, the next stage bootloader is present in the on-chip memory and the ROM code jumps to the beginning of that code. So that is your secondary program loader. So ROM code loads the secondary program loader into the SRAM in the phase 1 bootloading. So the ROM code is capable of loading a small chunk of code from one of the several pre-programmed locations into the SRAM. So If reading from all those memory fails, then it will try to read a byte stream from Ethernet, USB or UART. So the latter is provided mainly as a means of loading code into the flash memory during production rather than use in normal operation. So in SOCs where SRAM is not large enough to load a full bootloader like U-boot, there has to be an intermediate loader called the secondary program loader. So SPL. So the SPL must set up the memory controller and other essential parts of the system preparatory loading the third stage program loader into the main memory. So the functionality of the SPL is limited by its size. It can read a program from list of storage devices as can the ROM code, once again using pre-programmed offsets from the start of a flash device. So or a well-known file such as uboot.bin. So as the secondary program loader usually does not allow for any user interaction, but it may print various version information and progress messages which you will see on the console. So this diagram explains this phase 2, that is stage. So once it is in the secondary program loader, it is loading. So in the case of that is U-boot architecture, so again the SPL loads the that is your third program loader into the DRAM. So at the end of the second phase, the third stage loader is present in the DRAM and SPL can make a jump to that area. Now at last we are running a full bootloader like U-boot or the bare box. So once the third program loader, so there is a simple command line user interface that will let you perform the maintenance tasks such as loading the new boot and kernel images into the flash storage, loading and booting a kernel, and there is a way to load the kernel automatically without user intervention. So this third program loader, so it will be loading the kernel plus optional, that is file technology devices, and this init RAM disk into the SD-RAM. So this at the end of the third phase, there is a kernel in the memory waiting to be started. So embedded bootloaders usually disappear from the memory when once the kernel is running and perform no further part in the operation of the system. So this this is your regarding the bootloader. So your cross platform tools. So thank you for watching these bootloaders.